Okay, so what are the likely formulas for the following molecules? Well, NHOH. So how many hydrogens are in this structure here? Well, let's just start with the non-hydrogen atoms, so N and O. And there's probably going to be at least one bond between the nitrogen and the oxygen. And then since it has OH here at the end, we know that that hydrogen is bonded to the oxygen. Now, we know that oxygen has 6 valence electrons, and if we count half of the electrons in the two bonds here, so we have 1 electron here, and then, so that's 2, and then if we put 2 lone pairs in oxygen, that begins to look familiar. This is exactly the configuration of oxygen in water. But instead of 2 hydrogens, there's a hydrogen and a nitrogen. And so now this nitrogen likes to have 5 things bonded to it, or has 5 valence electrons rather. And so we want to start putting hydrogens in so that we can get to a point where if we have 1 hydrogen here, 1 there, and then a bond to the oxygen, nitrogen has 5 valence electrons. So let's count. We have 1 in this bond, 1 in this bond, 1 in this bond, so that's 3. And if we put a lone pair there, that would be 5. So the formula here is NH2OH. All right, let's look at B. So B, and I'll change color here. Why not? If I can. Maybe not. So B, Al, C with some, or Cl rather, and how many chlorine atoms would be around that aluminum? So aluminum, if we look at the periodic table, and I don't have it handy here, but if you look at the periodic table, you'll see that aluminum has 3 valence electrons. So let's just really quickly write out its electron configuration. It's 1s2, 2s2, 2p1. So its valence electrons are here in the second row, second energy level of the periodic table. So there are 3 valence electrons. All right, so if we have aluminum with 3, let's just put 3 electrons there. We can imagine that it's forming a bond to 3 chlorine atoms, and each of these chlorine atoms also contributes 1 electron. And so if we put in those electrons, we can write these 3 bonds to aluminum, and there we go, we're finished. Aluminum actually only has, in this particular case, where the aluminum is neutral, has no formal charge, and we'll get to formal charge in the next chapter. But in this particular formula, aluminum, Al trichloride, Cl3, the aluminum is only surrounded by 6 electrons total in its outer shell, 2, 4, 6. So it doesn't have a full octet, which kind of explains the high reactivity of aluminum chloride. And just as a little sort of prelude here, I'll change the color and put in another chlorine atom here. Let's just say chloride comes in. And if you mix aluminum trichloride with, let's say, water containing some chloride or some other solvent, what happens is this lone pair will come and add right in there, and you'll get, and this is just a little bit of a preview to what we'll be seeing, but then we'll have a new bond here to this chlorine, and I haven't drawn all the lone pairs generally we use this shorthand. I'll put the lone pairs on just so we can always remind ourselves that for the halogens, we're dealing with 7 valence electrons. So it has, each chlorine has 2, 4, 6 from the lone pairs, and then 1 contributing 1 electron into each bond. So 2, 4, 6, and then 7 contributing it to this bond with aluminum. And the same goes with all of the other chlorine atoms around this molecule. And then we're missing one thing, which is the formal charge here. So since chlorine, or chloride rather, brought in its lone pair here, we put a formal charge, usually a minus with a circle around it. You don't always have to put the circle around it, but sometimes it helps to distinguish it from other little scratch marks that might be on the page. But in this case, aluminum tetrachloride has an overall minus charge, and that's just a little preview to the formal charge that we'll be talking about later. So now let's go on to, let's see, we're doing C here. So this was A, that was B, and I will sort of shrink this down a little bit so we can move it over here, and then give myself a little room to do C. Why don't we do this one in blue? So C is CF2Cl question mark. So CF2 and then Cl question mark. Okay, so here we don't have any hydrogens. We have a carbon atom, so let's just draw the carbon atom first. And carbon has 4 valence electrons, so why don't we just put those 4 valence electrons around carbon. And then we have 2 fluorine atoms and 1 chlorine. And so if we add fluorine around, maybe I can change the color here. If we add fluorine, so let's just add those 2 fluorine atoms, and they're each contributing their electron. We still have 2 vacant sites essentially on carbon that can bond with something. And in this case, we're being asked to figure out how to get chlorine around there. So if we put 2 chlorine atoms, this looks like a happy molecule where carbon has a full octet. Let's count all the electrons, 2, 4, 6, 8, 8 electrons around carbon. And it has it's contributing its 4 valence electrons, 1, 2, 3, 4. And then the 2 fluorine atoms are contributing their red electrons. And then, of course, and the chlorine each also contributes its electron. And again, each of these, since both chlorine and fluorine are halogens, they're in the 7th column of the periodic table. And that means they have 7 valence electrons. And here we go. We have a molecule in which every atom has a full octet. So counting all the electrons surrounding each atom, you can see there are 8 electrons surrounding each of these atoms, and then including carbon in the middle. So that would be CF2Cl2. Okay, and lastly, we have D here, CHO. So how many hydrogens? And what does this molecule look like anyway? So D here. Crazy color scheme. Okay, I can't seem to find my other colors. Let me just get some more interesting colors here. Okay, I think we'll be able to grab some more interesting colors here. So The question is D, CH question mark O, CH. Well, let's draw in the non-hydrogen atoms first. So C, and I'll just put O up here, could put it anywhere, but carbon and oxygen, they're going to have at least one bond. Okay, so now let's look at the valence electrons around each of these, carbon and the oxygen. The carbon has 4 valence electrons, so one of those is in this bond here with oxygen, and then we'll put 3 others around. How many does oxygen have? It has, looking at where oxygen is on the periodic table, it has 6 valence electrons. So let's put oxygen in a different color here. So oxygen has one of its electrons in this bond, and then 2, 3, 4, 5, and then 6. So this is a little bit tricky. The single electron here and one of these single electrons around carbon suggests that maybe there should be a double bond here, because if these 2 electrons get together, let's just redraw this. Carbon and oxygen. And what if carbon, I guess I got the wrong color pink there. I wanted to keep that pink. Too many color choices here. Oh well. So if 2 of these electrons on carbon, this one and this one, come together with 2 of these electrons on oxygen, we can essentially make a double bond, and that would give us, at least as far as the oxygen goes, 2, 4, 5, 6 valence electrons. So oxygen has one of its valence electrons in this bond, 1 valence electron in this bond, and then all of its lone pairs. So 1, 2, 3, 4, 5, 6 around oxygen. And then if we just go ahead and count all of the electrons that oxygen has around it, including the ones that it's sharing with carbon, 2, 4, and then 2 electrons in this bond, and 2 electrons in this one, so 2, 4, 6, 8. So oxygen is happy, it has a full octet. Now carbon has 1 electron here, 1 there, and then 1 in this bond, 1 in this bond. So it's 4 valence electrons, fine. And then if we count the number of electrons around carbon, 2, 4, 5, 6, it could use 2 more. And we're looking for hydrogens here. So let's just add a hydrogen. Bring in a hydrogen there and a hydrogen there. And voila, we have, and I'll redraw it here, C, and I'm drawing it this way with these angles, sort of thinking ahead a little bit about geometry and the fact that this is a trigonal planar geometry here, because carbon has three things around it. 1 thing, 2 things, 3 things. But in this case, we're just asking how many hydrogens, so CH2O, and this is a molecule of formaldehyde.